covered the supervised learning algorithms, decision trees, and ensembles. A natural progression is to explore the complexity of neural networks and deep learning. Deep learning, neural networks. Deep learning is a subfield of machine learning that uses multi-layered artificial neural networks (ANNs) to learn complex patterns in large amounts of data. 1. Artificial neural networks (ANNs). ANNs are inspired by the structure of the human brain, consisting of interconnected nodes, neurons organized in layers. Input layer receives the initial data features x_1, x_2 dots x_n. Hidden layers perform intermediate processing. These layers apply weights and biases to the inputs, perform a summation, and then pass the result through an activation function like ReLU or sigmoid. Deep learning models have multiple hidden layers. Output layer produces the final result, e.g., probability of a class or a predicted continuous value. 2. Training the network, backpropagation and optimization. Training a neural network is an iterative process of adjusting the weights and biases to minimize the difference between the network's output and the true values, the loss function. Forward propagation, the input data flows from the input layer through the hidden layers to the output layer to generate a prediction. Loss calculation, the error, loss, is calculated based on the prediction. Backpropagation, the calculated error is propagated backward through the network. This process determines how much each weight contributed to the error. Optimization, an optimizer like stochastic gradient descent or ADAM uses the information from backpropagation to adjust the weights and biases, minimizing the loss for the next iteration. 3. Specialized deep learning architectures. Different network architectures are suited for different data types and tasks. Convolutional neural networks (CNNs), best for image and video processing. Key feature: use convolutional layers to automatically extract spatial hierarchies of features, edges, textures, shapes from pixels. Example: image classification, object detection. Recurrent neural networks (RNNs), best for sequential data where the output depends on previous elements in the sequence. Key feature: have an internal loop that allows information to persist, giving them a memory. Examples: time series prediction, speech recognition. Long short-term memory (LSTMs), a sophisticated type of RNN designed to overcome the vanishing gradient problem, allowing them to learn long-term dependencies in sequences. Best for language translation, text generation. Through the core ML process, evaluation, feature engineering, classic supervised algorithms, decision trees, ensembles, and deep learning, ANNs, CNNs, RNNs. A comprehensive next topic should address the crucial final stage of the ML lifecycle, model deployment and monitoring, and the vital topic of model interpretability and ethics. Model deployment and monitoring. This stage involves moving the trained model into a production environment where it can make real-world decisions and ensuring it stays accurate over time. 1. Deployment strategies. Offline, batch prediction. The model processes large batches of data at regular intervals, e.g., daily or weekly, and updates scores in a database. Use case: calculating customer churn scores overnight. Online real-time prediction. The model is hosted as an API endpoint, e.g., REST API. It receives a single request, makes a prediction, and returns the result immediately. Use case: predicting the classification of an uploaded image or recommending a product instantly. Edge deployment. The model is compressed and deployed directly onto a device, e.g., a smartphone, a drone, or an IoT sensor, without needing a constant internet connection to a server. Use case: face unlock on a phone. 2. MLOps, machine learning operations. MLOps is a set of practices that automate and manage the entire ML lifecycle from development to production. CI/CD, continuous integration, continuous delivery, automating the testing and deployment of the code and the model itself. Model versioning, tracking different versions of the model and the data they were trained on, allowing for easy rollback. Infrastructure, using cloud services like AWS SageMaker, Google AI Platform, Azure ML, or containerization Docker for consistent and scalable deployment. 3. Monitoring and maintenance. Performance monitoring, continuously tracking the real-time performance metrics, e.g., accuracy, latency, against the initial baseline. Data drift, monitoring if the statistical properties of the incoming live data have changed significantly from the training data. This often causes model performance to degrade. Concept drift. Monitoring if the relationship between the input features and the target variable has changed, e.g., changes in consumer behavior. This requires retraining the model. Model interpretability and ethics, XAI. As ML models are used for high-stakes decisions, e.g., loan approvals, medical diagnoses, understanding why a model made a decision is crucial. This is called explainable AI, XAI. 1. Interpretability techniques. Feature importance, quantifying which input features had the greatest influence on the model's overall prediction, especially useful for ensemble models like random forest. SHAP, Shapley Additive Explanations, a method based on cooperative game theory to explain the output of any ML model. It calculates the contribution of each feature to a single prediction. LIME, Local Interpretable Model Agnostic Explanations, explains individual predictions by creating a simple interpretable model, like linear regression, around the specific data point being analyzed. 2. Ethics and bias. Bias detection, identifying and mitigating biases in the training data, e.g., disproportionate representation of certain demographics that can lead to unfair or discriminatory outcomes. Fairness, ensuring the model's performance is equitable across different demographic groups, e.g., accuracy should not be significantly lower for one race or gender. Transparency and accountability, establishing clear protocols for who is responsible for the model's decisions and documenting the model's purpose, training data, and limitations. For our next topic, let's explore unsupervised learning in more detail, specifically focusing on clustering and dimensionality reduction. These are powerful techniques for finding hidden patterns in unlabeled data. Unsupervised learning, uncovering hidden patterns. Unsupervised learning deals with unlabeled data, meaning there are no predefined output variables. The goal is to discover inherent structures, relationships, or groupings within the data itself. 1. Clustering, grouping similar data points. Clustering algorithms aim to partition a dataset into groups, clusters, such that data points within the same cluster are more similar to each other than to those in other clusters. Use cases: customer segmentation for targeted marketing, document classification based on content, anomaly detection, outliers often form small distinct clusters, image segmentation, popular clustering algorithms, k-means clustering. How it works: iteratively assigns each data point to one of k predefined clusters. It works by 1. Randomly initializing k cluster centroids. 2. Assigning each data point to the nearest centroid. 3. Recalculating the centroids as the mean of all points assigned to that cluster. 4. Repeating steps 2 and 3 until the centroids no longer move significantly. Key parameter: the number of clusters kv must be specified beforehand. A scatter plot showing data points colored by k-means clusters with distinct cluster centroids. DBSCAN, density-based spatial clustering of applications with noise. How it works: groups together data points that are closely packed together, marking as outliers those points that lie alone in low-density regions. It doesn't require specifying the number of clusters. Advantages: can find arbitrarily shaped clusters and is robust to noise. A scatter plot showing data points clustered by DBSCAN, with some points identified as noise, outliers, and various irregularly shaped clusters. Hierarchical clustering. How it works: builds a hierarchy of clusters. It can be agglomerative, bottom-up, starting with individual points and merging them, or divisive, top-down, starting with one large cluster and splitting it. Output: often visualized as a dendrogram which shows the successive merges or splits and the similarity levels. A dendrogram from hierarchical clustering, showing a tree-like diagram of how data points are grouped into clusters. 2. Dimensionality reduction, simplifying complex data. Dimensionality reduction techniques reduce the number of features, dimensions in a dataset while trying to preserve as much essential information as possible. This is crucial for visualization, making high-dimensional data plottable, e.g., reducing to 2D or 3D. Storage efficiency, reducing the memory footprint of the dataset. Speeding up training, fewer features means faster training for subsequent supervised models. Mitigating the curse of dimensionality, avoiding issues that arise when working with very high dimensional data, such as data becoming sparse. Popular dimensionality reduction algorithms. Principal Component Analysis (PCA). How it works: a linear transformation technique that identifies the directions, principal components, along which the data varies the most. It projects the data onto a lower dimensional subspace defined by these components. Goal: to maximize the variance captured by each successive principal component. A 3D scatter plot of data points with arrows showing the first two principal components, indicating how the data's variance is projected onto a lower dimension. T. Distributed Stochastic Neighbor Embedding (TSNE). How it works: a non-linear technique primarily used for visualization. It maps high-dimensional data to a lower dimensional space, typically 2D or 3D, while trying to preserve the local structure of the data, i.e., points that are close in high dimensions remain close in low dimensions. Advantage: excellent for revealing clusters and separating complex manifolds that PCA might miss. A 2D scatter plot of data points clustered by TSNE, showing clearly separated non-linear clusters that might be difficult to see with linear methods.